Okay, so moving on to our plenary, we're delighted to have Steve Carpenter here today. I think for many of you, Steve probably doesn't need an introduction if you're familiar with the work that he's published over the years. Steve is Emeritus Director and the Stephen Alfred Forbes Professor Emeritus of Integrative Biology at the UW-Madison Center for Limnology. He's published 5 books and more than 450 scientific papers, book chapters, reports, and commentaries. I still remember the first ASLO meeting I went to. The only talk I remember from that meeting was a talk that Steve gave on trophic cascades. And I thought, what is this new paradigm of you can put fish in a lake and actually change what will happen to everything else in the lake? And that was just Steve getting started. We were both a lot younger then, but he's continued to develop new paradigms and challenge old paradigms throughout his career. And he's the epitome of an interdisciplinary limnologist, studying everything from nutrient biogeochemistry to trophic dynamics to the interface between natural systems and human behavior. He's one of the earliest scientists to consider the effects of global change on freshwater systems, and he's one of a handful of scientists conducting whole lake experiments that provide insight beyond what could be gained from conventional experiments and monitoring programs. He's furthered our understanding of how stressors can affect resilience and lead to alternative stable states in aquatic systems, something that had not received much attention in lake management programs previously. He also has worked on lake resilience and how it's affected by social and economic factors, which is especially relevant to the theme of this conference. Just a few of Steve's awards that he's received, to name a few: the 1999 G. Evelyn Hutchinson Award. In 2011, he was a laureate for the Stockholm Water Prize. 2015, the John Martin Award from the Association for Sciences in Limnology and Oceanography. 2019, the Margalef Prize. 2022, the Blue Planet Prize. I think if you go through the list of prizes and awards Steve's received, you'll come to the conclusion that the only reason he hasn't received more is because there's none left to give him. They've ran out of awards to give him. So we're excited to have him speaking at this meeting. As I mentioned, his work, especially over the last 2 decades, has considered the interactions between natural and socioeconomic systems, and he's promoted wise ecosystem stewardship not only through his research but through active participation in various initiatives, including the Water Sustainability and Climate Project, the International Science Advisory Council for the Stockholm Resilience Center, the Swedish Academy of Scientists Bayer Institute of Ecological Economics, the International Resilience Alliance, which focuses on assessing the resilience of coupled human and natural systems and developing tools that support sustainable development. Steve, thanks for agreeing to speak with us, and welcome.
Thanks. All right. Okay, you'll get that. Go for it. Thank you. It's blinding up here. I forgot my sunglasses, but thank you for that very kind introduction, Harvey, and thank you all for coming. I'm delighted to be here to talk about resilience. And while we're waiting for the slides to come up, most of the natural scientists, or ecologists at least, know that resilience has been around as an ecological concept for about 60 years, and there are rigorous ways of measuring it and comparing it across systems, and I'll cover those definitions when we get to the slides. And we're at the slides. Thank you, Jerome. About half of the talk is going to move into solving social ecological problems that involve resilience, and social scientists have picked up the idea and developed it in areas of management and innovation to a really unique extent, and it still has its roots in the ecological concept, but it's evolved in some very different qualitative directions, and I'll briefly touch on those. So I'm going to hit 4 topics today. First is definitions. Anyone here who is an experienced ecosystem modeler will know these definitions, so you could just take a short nap now, but others may want to be reminded of them. We're going to go through an example using a whole lake experiment on trophic triangles and trophic cascades. And this is just core limnological science. Then shift to a large-scale project on resilience of people and nature, and then I'll give you a summary. So first, definitions. The slide shows the rate of change of something, say chlorophyll in a lake, versus the concentration of chlorophyll on a log scale, and this characteristic S curve indicates alternate states. The 0 line marks increase from decrease, and so you can see that take the left solid colored point, if there is a slight perturbation to the left, the rate of change is positive and the system will move back toward the black solid point. If there is a shift to the right, the rate is negative and it'll move back to the right to the solid point. And that's the hallmark of stability. So in ecology, if the response to a small perturbation is to move back to the original point of origin, we call that a stable system. The central point, the second of the 3, the open circle, is unstable. So at that point, a slight perturbation to the right, say, results in growth and movement away from the open circle. A slight perturbation to the left results in a decrease in the rate and a shift away from the open circle. Those thresholds, points that are where the rate of change is 0, but they are unstable, the slightest perturbation causes them to move away, also turn out to be fundamental for thinking about resilience. This slide shows the left panel is the panel you just saw. The right panel is a potential diagram. If you integrate the rate of change curve, just take the area under the curve and change the sign, multiply it by -1, you get this ball and cup diagram. And the stable points appear as valleys, as cups. I put a coffee cup with a ping pong ball there to indicate stability. The ping pong ball will stay there unless you knock it out. And the unstable point is a hill. And these ball and cup diagrams are a fundamental tool for thinking about resilience, and they have a simple mathematical derivation. You just integrate the rate curve. The unstable point is a point where the water that's coming off that dog's ears could go to the left basin or the right basin, and it's pretty much random at the unstable point. So a droplet landing right at the unstable point could end up rolling either direction into either cup. Resilience is often measured as the width of the cup in, say, chlorophyll units in this case. It can also be measured in the average amount of time it takes for the system to move from the between stable points across the threshold. Now I'm going to give you an example. I want to turn to a specific example from lakes, and this concerns the trophic cascade, which Harvey mentioned in the introduction. And the question is, are the dynamics of trophic cascades capable of creating alternate states? Do cascades move an ecosystem across a threshold and thereby create alternate states? And about 25 years ago, the answer to that question was not known. And Jim Kitchell and Carl Walters and I spent many days arguing about it in field stations and fishing boats, and trying to figure out how could this possibly happen, what could go on that could create alternate states and an unstable threshold. And the idea we came up with is a trophic triangle. So the triangle is formed by adult piscivorous fish, the juveniles of that fish species, and a smaller bodied forage fish. At a high harvest rate by people, so if adult piscivores are being removed at a rapid rate, the system will shift to dominance by the forage fishes, by the planktivorous fishes, and the plankton will shift to small-bodied grazers, chlorophyll will increase. It's basic cascade dynamic. On the other hand, if there is a very low harvest rate of adult piscivores, they will come to dominate the ecosystem. There'll be fewer planktivores. We'll end up, the lake will have large-bodied grazers and low chlorophyll. Again, just a basic cascade result. And by the time and this sounds simple and obvious now, but 25 years ago it wasn't. And when we finally finished putting this together, Kitchell said, "That's right. You guys, we figured that one out." So we then turn to experimental tests. Can we demonstrate the cascade in a whole lake experiment? And the basic idea I'm going to show you one experiment in which we increased from zero, we gradually increased the number of piscivorous fish. So we went from the upper panel with no piscivorous fish to a situation where we had gradually, a few fish at a time over several years, increased the number of piscivorous fish to the critical point. And this was done in small lakes in northern Wisconsin that were heavily instrumented, so we got a ton of data. This diagram shows the expected transition. So I'm not going to spend a lot of time on this, but this shows a model result of our expectation, and the pale blue line has a critical transition point in it. It has a point where the rate just nicks the zero line, and those points are critical transition points from a system with only one equilibrium to a system with 3 equilibria, 2 stable, 1 unstable. When the attractor appears or disappears, when there's a critical transition between, in this case, 1 stable point and 2 stable points and an unstable point, they're using models. It's been shown that the external shocks cause bigger displacement and higher variance. And I'm not going to go through the math today, but I listed a couple of papers there you can look at. And we use these indicators so we would expect to see recovery from displacement goes to zero, actually. The autocorrelation or eigenvalue of the system goes to zero, and we would expect to see a big increase in variance of the system. And we would expect to see that at every trophic level because of the trophic cascade. And this diagram shows the result that we obtained. So we expected to see a big increase in the eigenvalue right toward 1 at the critical value of the harvest rate, and we also expected to see a big increase in variance, and that indeed occurred. This shows the experimental setup. So we're turning now from modeling to the lakes with a manipulated lake and a reference lake in northern Wisconsin. And the idea was to gradually add top predators to the manipulated lake from less than 20 largemouth bass in this case to more than 100 largemouth bass. And then we expected to see an opposite shift in the planktivorous minnows, a response in body size of the grazers, and a shift in chlorophyll. This shows some results, daily measurements of minnows, zooplankton, and chlorophyll in the lake. I'm not going to go through that in detail, but I'm going to show statistical analyses of some of the results. So the reference lake had only one stable equilibrium, and it had one stable equilibrium throughout the 4-year experiment. The manipulated lake, Peter Lake, showed 3 equilibria over the course of the 4-year experiment with the expected pattern of stability and instability. This slide shows the eigenvalues through time, and the manipulated lake is in red, the red and pink error bars. The reference lake is blue and the pale blue error bars, and the horizontal dotted line shows the critical transition point where the eigenvalue crosses 1, indicating instability. And the system became unstable early in 2010 in this experiment. My point in going quickly through this already published experiment is to show you that there's an established method for measuring resilience in ecosystems. You define the ecosystem. What are we talking about? What's the time frame? What components, interactions, and drivers are involved? Define the question, resilience of what to what. In this case, resilience of the food web to a gradual change in the apex predator. And you can't think about resilience without saying what's resilient and what the stressor is. Model the system to address the question. Whenever we run these large-scale experiments, we spend a couple of years building computer models of the system and exploring them to anticipate what might happen. Use the model to study the possible outcomes and design an experiment. I showed you a case where an experiment is possible. However, and it's not essential to do an experiment. There are many cases where big human perturbations have created a quasi-experiment, or where a natural catastrophe, a shift in the weather, a hurricane, or a volcanic event have created a shift. And in those cases, you can also analyze resilience if you have long-term data available. And once you've established the existence of a threshold and a transition point, you can estimate resilience as distance to the threshold, how big a push is needed to change, or statistics like exit time or survival time. So, it's people sometimes believe that resilience is a fuzzy, wishy-washy concept out there, and in ecology it isn't. It's a rigorous, measurable quantity of ecosystems. Now I'm going to shift to talking about resilience of people and nature, where the systems are much more complex. The dominant animal has very complicated behavior, social behaviors, political behaviors, and institutional behaviors. And the concept of resilience is still applied, but many of the ideas become verbal rather than quantitative, or pencil and paper sketches rather than quantitative. But the notion of resilience has spread through sociology, political science, psychology, and is now very common in management circles. The example I'm going to talk about is the Yahara watershed of southern Wisconsin, which contains the city of Madison. Many of you have probably been to Madison. You know it has multiple lakes. They're not great lakes, okay, but they're pretty good lakes. And there are 5 of them through the city, and a substantial human population, enormous amount of agriculture, extensive urban area, and a small percentage of natural vegetation. Lakes are the environmental centerpiece. One of our mayors once commented that without the lakes, we're just Omaha. And I apologize if anyone here is from Nebraska, but the mayor's point was that the lakes make the city a great place to live. And the lakes have problems. They're heavily polluted with agricultural runoff, and most aquatic scientists know how this works. We have a lot of dairy in the watershed. The animals, the dairy cows, receive feed that's full of nutrients and full of bacteria. Nowadays they get a lot of antibiotics to make them grow faster, and they consume a lot of water. And out the other end of the cow comes a lot of nitrate, more and more antibiotic-resistant bacteria, which are an increasingly severe health problem in groundwater throughout Wisconsin and other dairy states, and phosphorus. The phosphorus is not very mobile, not very soluble in the water itself. It mostly moves in particulate form and total phosphorus form. The nitrate tends to be dissolved, and all of those end up in the water. We're also seeing a wetter climate with more extreme storms. Madison has good climate data back to 1939, and here I've plotted the return time of a 100-millimeter precipitation event in one day. So that's about 4 inches in one day. And that's a substantial amount of rain. A couple of photographs from one of those storms are shown on the slide. The upper photograph is from campus, after one of those big rainstorms. And, you know, it sort of ruins your day to think you were going to be heading home, maybe pick up the kids at daycare and get some groceries, and your car is flooded. The lower photo shows a cornfield or former cornfield and a lot of nutrients running off that cornfield. So the Yahara watershed has seen a lot of change since the 1870s. In the 1870s, or before the 1870s, the lakes were fairly clear and surrounded by white calcite beaches, and that's no more the case. In the 1870s, agriculture developed in the watershed. A lot of Civil War soldiers came back. They were given land allotments to farm. The moldboard plow had been invented and was widely available. And there was a tremendous amount of erosion of topsoil into the lake. That topsoil was very rich in sulfate, and the sulfate immediately tied up the iron in pyrite, which is insoluble. And so and iron is an important regulator of phosphorus in lake water, as you all know. And without the iron, the phosphorus was free to roam and begin to cause water quality problems. Industrial agriculture with commercially produced fertilizers came in around 1950. Dairy and meat industries developed after high-intensity cropping became possible in the watershed. And now, starting in the 1970s, we're seeing more and more extreme precipitation, erosion of fertilizers and manure. The lakes are a lot greener with more blooms, more toxic blooms, and more costs to clean the water. This is a familiar story throughout the agricultural states of the United States. Around 2010, a group of us, well, actually several years before 2010, but an interdisciplinary group of limnologists, hydrologists, social scientists, artists, and writers got together and formed a project called Yahara 2070, aimed at understanding changes in land use, climate, and demand for land and water. How are those going to change in the future, and what does the future look like for future generations in the Yahara watershed? And can we steer that future in more desirable directions? And we focused on changes between 2010 and 2070. 60 years is a handy time unit. Most people can imagine change over a 60-year period through the dynamics of their own families. All of our results are posted at that website, and I'll remind you of the website again. So we started by asking people what they thought. Instead of grabbing our Secchi disc and our Van Dorn bottle and just running out there and doing a bunch of measurements, we talked to people about what they thought about the situation. And so we began with a survey approach and with a workshop approach. And through the survey and the workshop, we tried to study people's hopes and fears for the region. What do they want to preserve? What features would they like to change? What do they think is resilient? It's going to be difficult to change. It's probably going to persist. And what do they think is unstable? Because the things that are unstable are the points where change is easy. And especially the social scientists have numerical tools for analyzing this kind of data. And from the interviews and workshops, from the data we collected there, we began to cluster the beliefs that appeared, and we found actually a small number of clusters of what people thought about the future, and we could see some lines of fracture among the clusters. And for each of these, we constructed a plausible story with art about the logical consequences of each cluster. So to repeat, we sampled from a large number of people in the watershed, clustered the samples, and condensed them to a few scenarios. And we ended up with 4 stories that were initially told simply as stories, and then art was added to the stories, and then we added computer simulations on top of the stories and art. So we began with a qualitative and worked to the quantitative rather than the reverse. The motivating questions are written there. The first one is, what if we don't do anything? Second one, what if we increase our investment in green tech, education, try to manage better? Third, what if there's a generational shift in values that embrace environmental stewardship? And there are some indications that shift is occurring. Or what if governance treats clean water as a valued resource? So clean water becomes a product of agriculture, and farmers are rewarded for cleaning the water, for releasing clean water from their farms. And the idea was that we would, these stories would evolve over the 60-year period, and our first step was to write the stories like magazine articles, and then have another set of workshops and get feedback and iterate with people, try to make the stories believable, complete, and understandable, and that takes a while. Once, as the stories were beginning to take shape, we shifted to the quantitative analysis, and I'm not going to go through the models in detail, but I gave you two references there, and both of those references are about bridging from stories to quantitative analysis, and the models are all posted on our website, and due to shortage of time, I'm not going to go through the details today, but we had detailed biophysical models of air quality, water quality, land use and land cover change, and from those we could draw pictures, draw quantitative conclusions about what the Yahara was going to be like in 2070 under each of those scenarios. Just as one example, we looked at factors that affect direct drainage load to the lakes. The photograph shows direct drainage load happening in action there. There's been a storm and a lot of soil is running off into the lake. And we looked at 4 categories of factors: land use, land management, climate mean, and climate extremes as drivers of direct drainage load. And we found that it's the extremes. Even land management is important. It makes a difference, but you can't do as much with land management as will happen with extremes of rainfall. And these kinds of quantitative results were useful to Dane County as they underwent land use planning exercises and that sort of thing. So our goal was to broaden the discussion, just to have a better conversation throughout the watershed of what we want the future to be like and how we're going to get there. So we ended up with stories that are each one is illustrated, each one has a short video. We came up with a reader's guide for book clubs and church groups. Since the stories came out, which was about 2013 or so, we had a tremendous number of requests for workshops, and all of the PIs and many of the grad students from the project, presented these workshops to the public. There was a lot of interest, and many of these groups met in bars and churches, and I don't normally spend a lot of time in either bars or churches, but during those few years I was in those places a lot. We held a writing contest with Madison Magazine and Wisconsin Public Radio. The real novelists, actual published novelists, reviewed the stories, and the best ones were read on the radio and printed in Madison Magazine. Wisconsin Public TV did a TV special about the project. I mentioned the interviews and public presentations, hundreds of technical papers. We had model packages, and the model packages were actually taken up by some of the engineers who were working for the county on planning exercises, and lots of discussions with county executives and boards. So we put a lot of time into spreading the results. We uncovered a number of local actions that can help, and many of these limnologists know these already. Expand the area of native and perennial grassland, grow cover crops during the cool season, keep the soil in place, don't spread manure on frozen ground, and that is now banned in Dane County. Improve composting of manure, and there is a local farmers group that's doing on-farm experiments, or did on-farm experiments to improve composting. The county is in the process of building a network of 17 manure digesters that will be scattered around the county so that every farm is reasonably close to a digester, and it's not a long haul to take the manure over there for conversion to a lightweight fertilizer product that can then be shipped to a phosphorus poor region. The digesters also yield methane that is captured and used to run county vehicles. So it's a double payoff. Polluted sediment has been dredged from the major streams, and phosphorus in lawn fertilizer is now banned. So we've seen considerable progress since 2000 in the region, and but the phosphorus loads are not declining. We are essentially working against climate change, and the increase in extreme storms is continuing to move polluted soil into the lakes, and there's already a lot of phosphorus in the sediment of the lakes that can be recycled. So we're not, despite all that work, we're not yet seeing much benefit. I'm now going to give you just a quick summary of what I have said. First of all, I pointed out that stable states and thresholds are measurable properties of complex systems. It's not a vague, hand-wavy concept. It's something you can measure, and they can be measured for lakes. They can also be measured for political systems or economic systems, where you get quantitative data, or sociological systems by survey methods. Resilience involves a state and a stress. So resilience of you have to think about resilience of a state to the stress, and you have to specify the state and the stress in order to have the conversation. Resilience is about critical transitions, loss or gain of states where a threshold appears or disappears. And for social ecological systems like the Yahara, resilience can be built by conversation, stories, art, and science translated and shared among self-governed people in a democratic setting. And I think the project shows that. So with that, I'll stop there, and happy to take questions if there's time.
Maybe if we could turn the lights down a little bit so Steve can actually see if somebody's putting their hand up. And we'll have microphones that can be passed around to anyone who has questions. Steve, thanks very much. Even though the Yahara Lakes are not what we would typically call Great Lakes, I think we can all agree that we've learned a lot from what you and others have done on those lakes over the last several decades. And all of this is really extremely applicable to what's going on in the Great Lakes as well. So thanks very much. Thank you. So do we have any questions for Steve? I'll let you take over.
Mark Danning from Milwaukee, and take advantage of being right up front. I appreciated what you said. And here in Milwaukee, sturgeon have come back after 140 years. We have 55 sturgeon coming through the waterways now this year, and we have a group called the Sturgeon Protectors. Here's the question, given that. When you talk about resilience and how resilience is designed, when we talk to the Sturgeon Protectors and their native people, and they talked about 7 generations plan, right? And we've heard that. But for the Sturgeon Protectors, it was, we'll start measuring when the sturgeon reproduce, not when we as humans make a plan, it's when they reproduce. Just kind of wondering, when you're hearing about this and you're looking for one of those things that's going to be a resilience indicator, can sturgeon as a being be used to measure resilience, or do we need to look elsewhere for that for our river system?
Yeah, those are terrific points, and particularly in my work with the Resilience Network, the Global Resilience Network based in Stockholm, we have heard from many indigenous people around the world about how they build resilience and how they assess resilience, and I think I've learned a lot from them, and I think many of their ideas can be put into practice. I think that's true. I need to know more about sturgeon. We don't have them in the Yahara Lakes, but I'm sure you can. One example that I heard from a group that would be transferable to Lake Mendota is Native Americans in Alberta actually track the size distribution of walleye, Stysostedion, which is an important food fish in that region, as it is in Wisconsin. They track the size distribution, and they adjust the mesh size of the nets they use to let the correct number of spawners escape. And so they are combining the harvest with the management of the reproduction, the spawning, in a very clever way that, I have never heard of that being done in another fishery, but it's just a brilliant way of maintaining healthy walleye stocks in those lakes. Just one example.
If we consider our collective work as a river of knowledge that is moving along a channel, and it's reaching a delta of fertilized by the diversity of the people that work in it. We currently see that river undergoing a tremendous stress. Can you apply your models of resilience to predict or project how we should treat our current environment that will help us to protect our future environment?
So as I understand it, the question was, could you apply the idea of resilience to the global change issue? And there are a number of efforts to do that. There's a project in Western Europe called the Safe Operating Space Project, and the idea is to try to estimate the threshold for the Earth system for all of the various stressors that we put on it. And for climate, for example, the question would be, how far can you go with adding greenhouse gases to the atmosphere? And the answer turns out to be we've already gone way too far, and we need to dial back. But that kind of idea can be implemented and has been implemented. You're talking about politics?
Politics, that's right.
Yeah.
Let me just mention that at the ASLO meeting, that several of the award winners actually got up and gave up their time to talk about how we are under assault by stress. And your model has the opportunity to help us understand how to address that. That's what I'm asking.
There are people who work in that area. I am not one of them, but for example, there have been two fairly important analyses of the United States that have been published in the last decade or so. One is the growth of inequality. And the United States was a relatively, there are statistics for measuring wealth distribution, and the United States was fairly egalitarian after World War II and through the 50s, 60s, and 70s. And starting in the 1980s, when the income tax structure became more regressive, there was an abrupt shift from progressive to regressive income taxes. We became much more unequal. And the United States is now the most unequal of the rich countries. And political scientists have connected that, and sociologists have connected that shift to environmental problems and a number of our social problems. A related case, and this one was just published a couple of weeks ago, and I haven't studied the math closely, but it's a paper showing that trust has eroded in the United States over the last 20 or 30 years, and democracy depends on trust. You have to believe that your vote is going to count, for one thing, that the democratic system is going to operate, and you have to believe that everybody who's voting is thinking hard about the same complex problem and making a responsible, grown-up choice about it. And people are increasingly skeptical about the function of that system. And those changes make problem solving harder.
Great, thanks very much, Steve.